Hi, in this video I'll show you how to use a parallelogram to choose the right trigonometry for pretty much any forces problem. And by the way, do give it a look, even if you've tried using parallelograms before and decided you didn't like them at all. And this often happens. You might have decided that you prefer to stick with one triangle instead of two. And a single triangle can often be fine, and it is after all how you probably learnt to add and subtract vectors, as though the vectors are journeys, and then what we take to be the sum total of any two of them is just like going, as we say, as the crow flies, which is to say, a straight journey beginning and ending the same. And that's fine if it works for you, and if you never have any trouble deciding how to arrange the triangle. But with forces, that way the single triangle is missing a trick, which is that with a parallelogram you can always imagine the vector arrows as strings literally pulling, and in fact you draw them all as coming out from the same point, the same particle that they're pulling. And then it's totally natural and intuitive to see the middle string as having the same effect as the other two acting together. Imagine this one pulling at the same time this one is pulling. You know the particle will move roughly in this direction, somewhere in between. And then you can feel that the trigonometry is just going to make this more precise. Now you might have noticed a bit of cheek here. For a start, plenty of forces push, not pull. So that's a bit of poetic license. But also for the trigonometry to work as we feel it should, we must be pretending that the lengths of the strings depend somehow on how strongly they are pulling. Otherwise, how is trigonometry going to tell us the resulting direction of movement? And we don't normally make any such assumption. But yes, this is exactly what you do want to pretend. That you can see the strength of a pulling force in the length of the string pulling. And you'll find it's totally reliable, and you can feel sure that you've chosen the right trigonometry this way. Always sketch. It doesn't have to be a great sketch, something freehand or with a set square. Also go here to this drawing machine if it might help you at all for teaching or learning. And do let me know if it does, or if you have any questions or problems. Thanks. And now an example. Question 5. Three forces acting on a particle. The first force has magnitude Pn and acts horizontally due east. This could be P then. P newtons, I should have said. Pn. Okay, the second force has magnitude 5n and acts horizontally due west. So we've no idea if that's bigger or smaller. But the third force has magnitude 2p newtons and acts vertically upwards. So we have got the proportion of those, of p and 2p. Also, the resultant of the three forces is 25. Okay, so we're wondering whether this resultant of 25 is going to be like that or like that. Although it won't be going all the way in, it won't be either of those exactly, will it? If 5 is less than p, then we've got something like this. And if 5 is greater than p, we've got something like that. Let's have, and that's got to be 25, by the way. Let's label that. Okay, let's call that 25. And then the question is, are we like this, where the difference between p and 5, let's use a magnitude bar there. So we're saying the positive difference or absolute difference between 5 and p is that distance there, whereas this is 2p. So the question is this the situation, or is that the situation? And it's not easy on the face of it to see which one. We might spot though that we don't have to think about this too hard, because we could just do the algebra now and we'll get a sensible result, because we can see the algebra isn't going to depend on whether we're here or here. The algebra is Pythagoras, clearly. 25 apparently is the square root of the square of 2p plus the square of this, which is going to be the same, you know, whether it's 5 minus p or p minus 5, whichever of those is positive, the square is going to come out the same. So we don't have to fret about that. Although, notice, it can be fun to think about it. If 5 is equal to p, as we first said over here, because we didn't update that, did we, after saying, well, if this one is over here, oh dear, that must be because 5 is greater than p. You can see various things are going wrong then, because, I mean, 5 is what it is. Perhaps it would be less misleading to keep 5 stable and then let p get greater or less. The trouble is, well, either way, you know, if p is rather small, smaller than 5 like that, then 2p is shrinking as well, and it becomes rather difficult to see how that hypotenuse could be 25. And by the way, in that situation where they're equal, we know that the hypotenuse is going to be up there. The triangle disappears really, but then 2p must be 25, but it can't be if p is equal to 5. 2p must be 10. So that's an impossible situation, p being equal to 5. The question is which way to turn to make things doable, possible. We don't have to solve it because we can do the algebra. Nonetheless, that's impossible. And we did see, didn't we, that this is impossible too, because these are getting too small for a plausible diagonal or hypotenuse here of 25. Whereas over this way, it looks as though this could be right. Let's find out by just getting down to the algebra. So we're saying square of 25 has got to be equal to the square of 2p, or 4p squared, plus 5 squared minus 10p plus p squared, which is going to tidy up to make 5p squared minus 10p equals 600, or indeed divide through by 5. In fact, let's make it all equal to 0. And factorise, which is 10 and 12, different signs, minus 12. So the only possible value for p is 12. And then this one is making a lot of sense, isn't it? Because the absolute value of 5 minus p is going to be a p-value of 12 minus 5, or 7. And yes, 2p is going to be 24, so we've got a 7, 24, 25 Pythagorean triple. A nice result. So P is 12, and the resultant and the vertical, let's call it theta, is going to be reverse cos of 24 over 25. Let's find out what that is. 24 over 25, and inverse cos of that, 16.26 ish, or 16.2, I mean 3 degrees to 3 significant figures. And the acceleration of the particle, and state the direction in which it moves. The particle has mass 3 and the coefficient of friction, yeah. So we know that the friction holding it back is going to be 0.15 of 3g minus 24. So the reaction, let's do that. G 29.4, 0.81. Meaning that the net force eastwards is going to be, and again it's a similar principle to this addition and subtraction here with the momentums really. We're saying the net force with which the particle is going to move is going to be the force given it by this component of the resultant of those 3 forces. In other words, the resultant of the 2 horizontal forces, 5 and P, which of course is 12 minus 5 is 7. The force with which the particle is actually moving is going to be 7, that propelling force of 7, minus this retarding friction of 0.81. In other words, it's going to be 6.19. And not only is it 6.19, but it's MA, or 3A, in this case, 3A, which is 6.19. So we might as well mention that. So finally we can say the particle moves eastward, and A equals a third of 6.19, or 6.19 over 3. Which is like going to be 2.06 and a bit. 2.06 to 3 significant figures. There we are. Okay, question 6.